Welcome to Educator.com. In today's lesson, we're going to discuss solving quadratic equations by graphing. In previous lessons, we talked about solving linear equations by graphing, a set of linear equations. Here, a technique can be applied to solve quadratic equations by graphing. Recall that the standard form of a quadratic equation is ax squared plus bx plus c equals 0, where a does not equal 0, because if a were to equal 0, then this x squared term would drop out and you would no longer have a quadratic equation. Also, and just to mention, another name for quadratic equations that you may hear are second degree equations. So this is the standard form of such an equation. Let me give you an example. An example of a quadratic equation would be something such as negative x squared minus 2x plus 3. Okay, so that would be a quadratic equation. Now, we can solve such equations by finding the x-intercepts of the graph of the corresponding quadratic function. In a previous lesson, we talked about quadratic functions, and we talked about how to graph those functions. So if you need review on how to graph a quadratic function, then you can see that in the previous lesson, and now we're going to apply that to solve the quadratic equation. So if this is my quadratic equation, the corresponding function would be y equals minus x squared minus 2x plus 3. Okay. What this is saying is that the x-intercepts of the graph for the corresponding function give you the solution or solutions for this quadratic equation. So here I have my equation, I have my function. Now I'm going to go ahead and graph it. A equals negative 1, B equals negative 2, because this is in standard form, so this is A and B. Let me find the x coordinate for the vertex. And recall that that's given by the formula negative b over 2a. So the x coordinate is going to equal negative 2 over 2 times negative 1, which is going to equal negative times negative, that's a positive 2 over negative 2 or negative 1. Now, to find the y coordinate for the vertex, I'm going to find f of negative 1. That's going to equal the y coordinate for the vertex. So looking up here at the function, this is going to equal negative x times negative 1 squared minus 2 times negative 1 plus 3. Don't need the x there. Negative 1 is the x value. Okay, so f of negative 1 equals negative 1 times negative 1 is 1. So it's going to be negative 1. So this comes out to 1. Then we have a negative sign in front of it. That's negative 1. Negative 2 times negative 1 is positive 2 plus 3. So this is going to equal 5 minus 1 is 4. So the vertex, the coordinates for the vertex are negative 1, 4. Remember also that when a is less than 0, you're going to have a parabola that opens downward. So I know it faces downward, and the vertex is at negative 1, 4. So the general shape is going to be like this. Go ahead and find some x, choose some x values, and find this corresponding y by substituting those into the function. So when x is negative 2, you get negative 2 times negative 2 is 4. The negative of that is negative 4. And this would be negative 2 times negative 2, that's positive 4. So the 4's cancel out, and that's going to leave you with 3. we already have when x is -1, we know that y is 4 because this is the vertex. Okay, when x is 0, these two terms drop out, and that leaves me y is 3. When x is 1, what I'm going to get is that I'm going to have a -1 plus 2 plus 3. Actually, -1 minus 2 plus 3. And this is -3 plus 3. Cancels out. I get a 0. And when x is 2, y is -5. So I have enough points to go ahead and start plotting. When x is -2, y is 3. When x is 0, y is 3. When x is 1, y is 0. And when x is 2, y is -5. So I have some points. And there's going to be another point about over here. If you think about the axis of symmetry, I'm going to have another point over here somewhere. So I have the general shape. And what I want to look at is the x-intercepts. So this is where the x value intersects with the graph. And that is one of the solutions for this equation. Now, x equals 1 when y equals 0. So one of my solutions is x equals 1. Let's talk about this second solution. I just kind of said, oh, this axis of symmetry, it looks something like this on the left side. But here I can actually use the axis of symmetry more precisely to find my other x-intercept. So let's look over here at what we have. I know that the axis of symmetry passes through here. When x is -1, y is 0. And I also know that if I increase x by 2, I'm going to have a point right over here, also at y equals 0. Well, by reflection, I know that if I decrease x by 2, y is going to be 0. I'm going to have a mirror image point on this other side. This is 2 away right here, and this is 2 away from the axis of symmetry right here. And I could do the same thing for other points. If I had one side, I can get the other. So since I did happen to have one of the x-intercepts, I could figure out the other one. And that's at -3, 0. So my two solutions are x is 1 and x is -3. So you can solve a quadratic equation by graphing out the corresponding function and then finding the x-intercepts. And the x-intercepts give you the x values that are solutions to the equation that you're working with. Now I mentioned solution or solutions, and what we just saw is that there were two solutions, and that is one of the possibilities. So a quadratic equation may have two distinct solutions. Another term that you'll hear when we're talking about solutions for a quadratic equation is roots. So instead of saying that's the solution, we sometimes say that's the root or roots of the quadratic equation. And for a lot of the graphs you'll see, it might be something like this or like this. And then I'll see, okay, these are my two solutions. These are my x-intercepts. So here x equals 1 and x equals 4. So my solutions are 1 and 4. Over here, this didn't land right on an integer, but that's fine. The solutions are not always integers. So anyways, wherever the x-intercepts are, if there are two x-intercepts at different points, this gives you two distinct or different solutions, unique solutions, or roots. That's the first possibility. The second possibility is that you get what's called one double root. And that occurs when you have two identical solutions. This is different than saying, oh, we have one solution. What we actually have are two solutions, but they're the same value. And in that case, we call this a double root. So you only end up with one unique value, but it's the result of two solutions. And later on, we'll discuss why it's two solutions and not just one solution, instead two identical solutions. Anyway, let's think about when this could occur. it would have to occur in a situation where there is only one x-intercept. Let's look at just a very simple function, a simple quadratic equation, and its corresponding function. So a quadratic equation, x squared equals 0. The corresponding quadratic function is y equals x squared. So here we have a quadratic equation. And here we have the corresponding quadratic function. Okay, first, when I'm graphing, I always look for the vertex, and I know that for the formula for the vertex, the x-coordinate is going to equal negative b over 2a. Here, I have a equals 1 and b equals 0. There's no bx term, so ax squared plus bx plus c equals 0. That's a quadratic function in a quadratic equation in its standard form. Here I have my a term, because a is not allowed to equal 0, or it's not a quadratic equation. So I do have an a term that is not 0, and it's 1. But the b, there's no bx here, so the b must have been 0 and the x dropped out. Same with the c. So what I'm left with is x equals negative 0 over 2 times 1. 0 divided by number is 0. So the vertex is at x equals 0. To find the y for the vertex, the y value, I'm going to find f of 0. And f of 0 equals x squared, so it equals 0 squared, or 0. So the vertex is at 0, 0. It's actually at the origin. Now, let's do a few points just to see what happens. And since a equals 1, I know this is going to curve upward. When x is negative 2, y is x squared, so y is 4. When x is negative 1 times negative 1 is 1. We already said when x is 0, y is 0. When x is 1, y is 1. When x is 2, 2 times 2 is 4. Okay, so I have my vertex, and that's negative 2, 4 is my second point. Negative 1, 1, 1, 1, and finally when x is 2, y is 4. So I have enough points to work with. Now, going back to what we were discussing, a quadratic equation may have two identical solutions called a double root. And this is represented graphically by when you have one x-intercept. And the time that would occur is when the vertex is on the x-axis. So you have only one x-intercept when the vertex is on the x-axis. Because if I were to have, say, the graph came out over here or a graph over here, it's crossing at 2 points. However, at the vertex, at the tip, if it intersects right at the vertex, like this one does, you're only going to have one x value. The two solutions are identical. And here, the solution is x equals 0. The solution for this equation that I gave is that x equals 0. Okay, we talked about when there are two unique solutions, and that's when you have the parabola intersecting the x-axis at two unique points. We have when there is only one unique solution, or a double root, two identical solutions actually, two identical solutions, which means that there's only one unique number, and that is when the vertex is on the x-axis. So the x-intercept is the vertex. Finally, you may have a situation where there are no real solutions. There are solutions, but they're not real numbers. Let's think about when that could be. Okay. for example, taking a quadratic equation, x squared plus 1 equals 0. That's my quadratic equation. My corresponding function looks like this. Find the vertex. Equals negative b over 2a. Here, a equals 1, and there is no b. Or there is a b, it's 0. There's no bx term. Standard form, ax squared plus bx plus c equals 0. Here, I'm seeing that I have ax squared. There's no bx term, it's actually bx. There's no bx term, so b must be 0. And I do have a c term. So the vertex is going to be negative 0 over 2 times 1, or 0. To find the y value of the vertex, you're going to find f of 0, and f of 0 equals 0 squared plus 1, or 1. Okay, so the vertex is at 0, 1. There's the vertex. And this is going to curve upward because a is positive. Finding some x and y values. When x is negative 2 squared is 4 plus 1 is going, so negative 2 squared is 4 plus 1, that's going to give you 5. When x is negative 1 squared is 1 plus 1 is 2. When x is 0, y is 1. We already knew that. When x is 1, y is 2. And when x is 2, y is 5. Okay, so when x is negative 2, 1, 2, y is 5. When x is negative 1, y is 2. When x is 0, oops, graphed that incorrectly. When x is 0, y is 1. So the vertex should actually be right here. Okay. When x is 1, y is 2. When x is 2, y is 5. So when I graph this out, this is what I find. Again, the vertex is at 0, 1. 0, 1, so it's right up here. And what this shows me is that there are no real solutions for this quadratic equation. Recall that if you're solving a quadratic equation by graphing, what you're going to find is that the solutions are the x-intercepts. You may have two distinct solutions. You may have one identical solution. Here, there is no x-intercept. This vertex is a minimum. Y is never going to go below that. And here, we have a y value of 1. In order to get an x-intercept, y has to equal 0, but it's never going to get that low. This is just going to continue upward. So in this case, there are no x-intercepts. There are no real solutions. One of the limitations of graphing is that if the solutions are not integers, it's very difficult to get an exact solution. If it doesn't come out right on an integer, the x values, the x-intercepts, if they don't come out right on the integers, then it's hard to tell on a graph the exact solution. In that case, what we do is we estimate the solution. That may be the best you can do if you're using the graphing method. For example, I may come up with this. And I do have two distinct solutions. I have two x-intercepts, but I can't give an exact value based on this graph. What I can say is that one of the solutions, call that x1, is greater than 2, but it's less than 3. So it's between 2 and 3. I have another solution. I'll call that x2. And I can say that x2 is greater than 3, but it's less than 4. So the best I can do is I can state it as an inequality like this, or I can give an approximation that it's approximately equal to, say, 2 1/4, but I can't give an exact value. And we'll learn some other methods later that don't have such a limitation. First, we're going to solve the following quadratic equation by graphing. X squared minus x minus 6. I need to find the corresponding function in order to graph, and that's y equals x squared minus x minus 6. I know that a equals 1, so I know that this opens upward, since a is greater than 0. I'm going to find the x value, x coordinate of the vertex, by finding negative b over 2a. So a equals 1 and b equals negative 1. Okay, so this is going to give me negative 1 over 2 times 1 is going to equal, negative times negative is positive, so the vertex is at x equals 1/2. To find the y value of the vertex, I'm going to get f of 1/2, which equals 1/2 squared minus 1/2 minus 6. So f of 1/2 equals 1/4 minus 1/2 minus 6, which is 1/4 minus 2/4 minus 6, which equals 1/4 minus 6. So that's minus 6 and 1/4. So the vertex is at x is 1/2, y is minus 6 and 1/4. So not the easiest thing to work with, but it gives me, some idea of where it's going to be at. So that's 5, 6 is, negative 6 is here, 1/4 is going to be about here, and then 6 1/4 right about there. And this opens upwards. This is my minimum. Now, what I'm really looking for, though, are the x-intercepts. I'm looking for the x-intercepts because I want the solutions to this equation. So I'm going to keep that in mind. Find the x-intercepts. I want to find some values for x where y is 0. I may have 2 distinct ones, 1 double root, or I may have no solutions. So I'm going to pick some points, some x values in the region of the vertex, and the x value for the vertex is 1/4. So I'm going to pick some values in that region. And what I really want to see is this graph. I know it's curving upward, and I want to know when is it going to cross the x-axis. All right, when x is negative 2, I would get y is 4. Negative 2 times negative 2 is 4. Negative 2 minus in front of that is going to give me a positive 2 minus 6. So 4 plus 2 is 6 minus 6, y is 0. Good, I already have one x-intercept. I have a solution right here. I got lucky. One of my points happened to be that I chose was right on the x-intercept. Now, the next one, when x is negative 1, y is negative 4. When x is 0, y is negative 6. When x is 2, y is negative 4. Okay, so when x, I already graphed this. When x is negative 1, y is negative 4. When x is 0, I have my vertex. Oh, I have my vertex already, but when x is 0, y is negative 6. I have my vertex right near that. So I know that that's going to be the minimum right here. And then when x is 2, y is negative 4. So I see I don't quite have enough points. There's a couple things I could do. I could graph some more points, or I could use reflection, but either one could be done. And if you look, it's going to be a little tricky because of where the vertex is. So let's go ahead and do one more point. When x is 3, I'm going to get 3 times 3 is 9, minus 3 minus 6. So that's 9 minus 9 is going to give me 3, 0. And I'm happy to see that that is another x-intercept. So this is one solution, this is the other. And this is x is negative 2, y is 0. This is x is 3, y is 0. Therefore, my solutions are x equals negative 2 and 3. And you can always check these by plugging the x values back in and making sure that what you get is a 0. So you can put these back into the original equation just to double check your math. Okay. Again, we're asked to solve a quadratic equation by graphing. The first thing I notice is that this is not in standard form. This is standard form. So first, put this in standard form. In order to do that, I'm going to subtract both sides by 4x. Because I want to move all these terms to the left and have everything equal to 0. Now I'm going to rearrange these so that it's in standard form. X squared minus 4x plus 4 equals 0. Okay. So this is my quadratic equation. The corresponding quadratic function is y equals x squared minus 4x plus 4. And I'm asked to solve by graphing. When I graph, I find the vertex. And the x value for the vertex is going to be negative b over 2a. Here I looked at this in standard form, and I have my function in standard form. That's why it needs to be in standard form, so you get the correct a and b values to use this equation. And since a equals 1 and b equals negative 4, I'm going to find that x equals negative 4 over 2 times 1. Negative times a negative is a positive. 4 halves equals 2. To find the y value for the vertex, I'm going to find f of 2. So f of 2 equals 2 squared minus 4 times 2 plus 4. That equals 4. 2 times 2 is 4. Minus 8 plus 4. So 4 and 4 are 8. Minus 8 leaves you with a 0. Okay. Coordinates for the vertex. X is 2. Y is 0. So when x is 2, y is 0. The other thing I notice is that this has an a that is positive. So the parabola opens upward. And I don't even need to waste time graphing out more points. I know that the vertex is here, and I can just sketch this out just to show you. If it would have opened downward, it would have been the same idea. It didn't really matter, but at least now you have some idea of the graph, and that this is my solution. I have only one unique solution. I have a double root. And this solution is that x equals 2. The reason that I have a double root is because the vertex is at the x-intercept. So I don't have 2 x-intercepts, I only have 1 x-intercept. So the solution is x equals 2. Third example. Again, I have to put it in standard form. This is not in standard form. I'm going to add 1 to both sides. So again, reminding you that standard form is ax squared plus bx plus c. Now this is in standard form, and the corresponding function is x squared plus x plus 1. Okay, graphing. Let's find the vertex. So the x value for the vertex equals negative b over 2a. Here, looking at it in standard form, a equals 1 and b equals 1. If I did not have this in standard form, I could make a mistake. For example, if this b value was over here, and I just looked at it in that form, I would have gotten the wrong value. Now, I also know that this opens upward since a is a positive value. So let's go ahead and find the vertex. So x equals negative b over 2a at the vertex. X equals negative 1 over 2 times 1, or negative 1/2. Okay. Now, for f of negative 1/2, that's going to give me my y value for the vertex. This is going to equal negative 1/2 squared plus negative 1/2 plus 1, which is going to equal 1/4 minus 1/2. So negative 1/2 times negative 1/2 is 1/4 minus 1/2 plus 1 equals 1/4 minus 2/4 plus 4/4. I'm going for the common denominator. So 1/4 minus 2/4 equals negative 1/4 plus 4/4 equals 3/4. So at the vertex, y equals 3/4. Right, the vertex up here, so it's nice and clear. The vertex is at negative 1/2, 3/4. Okay, negative 1/2 is here. 3/4 is right about there. I could graph some more points out and make a nice graph, and then what I would realize is that I have no real solutions. But instead of taking up all that time graphing, I'm just going to look at what I have. Whenever I have a vertex, I always stop and think, is this a maximum or a minimum? And recall that I said that since a equals 1, this opens upward. What I have here is a minimum. So this vertex is a minimum value. It's the minimum value of y. Therefore, this graph is going to curve upward as such, and it is never going to intersect the x-axis. I know that because in order for us to have an x-intercept or 2 x-intercepts, we have to have y equals 0. Some value of x for which y equals 0. But since the smallest that y is ever going to get is 3/4, there won't be any x-intercepts. Therefore, we have no real solutions. So when you're asked to solve by graphing, put the equation in standard form, find the corresponding function, and then find the vertex. Once you've done that, plot the vertex. Then you look at it and you say, okay, is this on the x-axis? If it is, you have your solution. You have your double root. If it's not on the x-axis, then you look at where the point is at and you see, does the parabola open upward and downward? And will that shape of a curve result in some kind of intersection with the x-axis? If it will not, then you're done. There are no real solutions. If it will intersect with the x-axis. Then you need to go on and find where those points of intersection are. This time we're asked to estimate the solution by graphing. So that indicates to me that these solutions are not going to be integers. And so for graphing, the best I can do is to estimate. Putting this in standard form, 6x squared plus x equals 2. Subtracting 2 from both sides. Now I have an equation in standard form with a corresponding function in standard form. All right, so let's go ahead and think about what we have here. We have a equals 6 and b equals 1. Vertex. The x value for the vertex is going to be negative b over 2a. So x is going to equal negative 1 over 2 times 6, negative 112. Well, this is going to be kind of messy to find the vertex. And what you need to think about is that you don't really have to have that exact value for the vertex all the time, because what you're really looking for is, when you're estimating, just an approximation of where the graph is going to cross the x-axis. So I always start out by looking for the vertex, and the vertex can be very helpful. It can tell you, do you have solutions? Do you have 2 solutions? Do you have 1 solution? No solutions. But when it's messy like this, sometimes it's best to just go ahead and have some points. Find some points and see if you can get your estimate that way. Because really all I need out of the graph is the intersections. I don't really need the vertex. I need this and this. So let's work from here and try to find some points that are a bit easier to work with. Okay, when x is negative 2, if I figure this out, I end up getting a big value where y is 20. Okay, when x is negative 2, y is way up here. So I'm going to try another value. When x is negative 1, I get negative 1 times negative 1 is 1 times 6, so that's 6 minus 1 minus 2. So that's negative 3. 6 minus 3, so give me a y value of 3. When x is 0, these two drop out, and y is negative 2. When x is 1, 1 times 1 is 1, times 6 is 6. 6, excuse me, right here. 1 times 1 is 1, times 6 is 6. So 6 plus 1 is 7, minus 2 is 5. All right, I have some points to work with. I'm going to leave that one off because it's way up here. And I have negative 1, 3. I have 0, negative 2. Okay. And then I have 1, 5. Now, I don't have a vertex. I don't know exactly what this is going to end up looking like. But I do know a couple of things that are important. Let me graph this a little bit better. I know that when I have a value of negative 1, y is positive. And then when I have an x value of 0, y is negative. That means that somewhere between negative 1 and 0, this graph crossed the x-axis. Therefore, I have a solution right here. I also know that when x was 0, y is negative 2. And that when x is 1, y is 5. So somewhere between 0 and 1, this crossed over from negative to positive. I don't know where, because graphing is not exact, but I do know that somewhere between here and here, and somewhere between here and here, lie the x-intercepts. Therefore, if I'm going to estimate, I'm going to say that x1 is greater than negative 1, but less than 0. And I know that because here y is positive, here y is negative, so somewhere in here it crossed. I know that for x2, x2 has to be greater than 0, because at 0, y is negative, and then suddenly at 1, it's positive. So there was a crossover. But it's less than 1. So when you're estimating, what you need to know is an approximation, that it's between these two integers. I can't get an exact value using the graphing method. So that concludes this lesson on educator.com, and we're going to be going on in future lessons to discuss more methods of solving quadratic equations.